210 is on limiting reactants, and we are looking at the foundations of chemistry, part 2, FC3, using stoichiometry to determine the relative amounts of substances consumed and produced in chemical reactions. You will learn how to determine the limiting and excess reactants in a variety of chemical reactions through stoichiometric calculations and experiments. A hypothetical situation here, a plain bologna sandwich consists of 2 pieces of bread, 1 slice of bologna. You're given 1 package of bologna that contains 8 slices of bologna and 1 loaf of bread that contains 30 pieces of bread. If we think of the sandwich making as a chemical reaction, the reactants will be the bologna and the bread, and the product will be the sandwich. Based on this information, what's the maximum amount of sandwiches that can be made? We can make 8 sandwiches. Which reactant is limiting? The bologna. Since it's a smaller amount and it gets used up, it limits the amount of sandwiches that can be made. Which reactant is in excess? The bread. Since it's a larger amount, it doesn't get completely used up and there's plenty of bread left over. Chemical reactions behave in the same fashion. There's often a reactant that gets completely used up in the reaction. This reactant limits or determines the amount of products that can be produced. On the flip side, the other reactant is often found in large excess amounts. This reactant in excess, that is, there's more of it present than there's needed in the reaction. Therefore, there will be some of it left over after the reaction takes place. In chemistry, it's crucial to learn how to determine which reactant is limiting and which is in excess. This is also known as limiting reagent or limiting reactant. It refers to the reactant that gets completely used up in a chemical reaction. The reaction is the one that limits or determines the amount of products that can be produced in a reaction, and it must be determined using stoichiometry. The only time you will need to determine limiting reactant is when the question gives you information about 2 reactants. If we look at the following example, methanol, CH3OH, which is used in a fuel in racing cars and in fuel cells, can be made by the reaction of carbon monoxide and hydrogen. So carbon monoxide plus hydrogen yields methanol. Suppose 356 grams of carbon monoxide and 62 grams of hydrogen are mixed and are allowed to react. What is the mass of methanol that can be produced? And what's the mass of the excess reactant that remains after the limiting reactant has been consumed? We approach these very similarly to regular stoichiometry questions. We write our balanced chemical reaction. CO plus H2 yields CH3OH. And we check if it's balanced. We have 1 carbon, 1 oxygen. We have 4 hydrogens, so we need 2 more hydrogens here. Now we have a balanced chemical reaction. We write our knowns and unknowns. We have 356 grams of carbon monoxide and 62 grams of hydrogen. And we're looking for how much methanol is produced. So here we have 2 different numbers given to us. This is a limiting reaction question, so we're given information for 2 of the reactants. Now, in order to figure out what mass of methanol can be produced, we need to figure out which reactant is limiting. So the easiest way to do this is to do a stoichiometry question on both the carbon monoxide, use the carbon monoxide grams, find how much mass of methanol is produced, and then you do a second stoichiometry calculation with 62 grams of hydrogen and find the mass of methanol produced and figure out which one's smaller, because that would be the one that's limiting, right? With the bologna, we can only make 8 sandwiches because we have 8 pieces of bologna. You know, if we used bread, we would have been able to make significantly more 10 sandwiches. Our bologna was limiting because it could make less sandwiches. That's what we need to do here. So we do these stoichiometry calculations twice. And we know since this is grams, we're going to need to find the molar mass of all three of our compounds. So we look, and carbon is 12.01 plus oxygen, which is 16. We get a molar mass of 28.01 grams per mole. For hydrogen, it's 2.02 grams per mole. And for methanol here, we have one carbon, which is 12.01. We have 4 hydrogens, which is 4.04. And we have 1 oxygen. So we have 12 plus 4.04 plus 1 oxygen, which is 16. And we get 32.05 grams per mole. All right, so we have to do 2 stoichiometry calculations here, starting with carbon dioxide. Well, it doesn't matter which one you start with, but we'll start with carbon dioxide. We have 356 grams of carbon monoxide, and we need to convert it to moles using our molar mass, 28.01 grams of carbon monoxide over mole of carbon monoxide. We use our molar ratio. You have 1 mole of carbon monoxide to 1 mole of methanol. That's what we're looking for. OH. And then we convert back to grams to figure out how much methanol we would produce if we use carbon monoxide. 32.05 grams of methanol over a mole of methanol. Just double checking, everything cancels off, and we're left with grams of methanol. So we found that we have 356 times 32.05 divided by 28.01. We get 407 grams of methanol. There we go. And we do the same thing for our hydrogen. But this time we start with 62 grams of hydrogen, and we use a molar mass to convert to moles. We use our molar ratio. We have 2 moles of hydrogen, goes on the bottom to cancel out for 1 mole of methanol. And then we convert back by using our molar mass of methanol. And if we work that out, we have 62 times 32.05 divided by 2.02 and 2. We get 492 grams of methanol. So if we look here, our carbon monoxide is limiting because it makes less methanol. Just like our bologna was limiting, it would make less sandwiches. That was the limiting reactant. Our carbon monoxide is limiting. So what I like to do is I like to put a box around carbon monoxide. If I have future calculations that I need to do with this question, it always has to be with our limiting reactant. We cannot use our excess reactant anymore when we're starting with a when we're starting with a number. But part B says what mass of the excess reactant remains after limiting reactant has all been used up. So now we are trying to find how much hydrogen remains after the carbon monoxide is used up. So what we're going to do is we're going to start with carbon monoxide again. So 356 grams of carbon monoxide, and we are going to figure out how much we actually needed of hydrogen. So that was 62 grams is too much hydrogen. We need to figure out how much we actually need. And we're going to use stoichiometry to find out how much hydrogen we need. So again, we go through. We convert to moles. We use our molar ratio. We have 1 mole of carbon monoxide and 2 moles of hydrogen. And then now we have to figure out how much hydrogen we actually needed in grams. We use our molar mass of hydrogen, moles of hydrogen, and 356 times 2 times 2.02 divided by 228.01, we get 51.3 grams of hydrogen. So we only needed 51.3 grams of hydrogen, but we actually had 62 grams of hydrogen. So 62.0 minus 51.3, so this is how much is needed. And we actually have 62 grams. We're going to have 62 minus 51.3. We'll have 10.7 grams of hydrogen left over. So these questions, a lot of work, but not really much different than what we've already learned. And our next example here, when copper 2 chloride reacts with sodium nitrate, copper 2 nitrate and sodium chloride are formed. Write the balanced chemical equation. So we have our equation here. Let's make sure it's balanced. I'm going to rewrite it. We have copper 2 chloride plus sodium nitrate yields copper 2 nitrate plus sodium chloride. I notice we have 2 nitrates, so we'll need a 2 in front of our sodium nitrate. And then we'll need a 2 in front of sodium chloride. We then write our knowns and unknowns. So the 15 grams of copper 2 chloride, 15 grams of copper 2 chloride react with 20 grams of sodium nitrate. How much sodium chloride can be formed? We know we're going to need to calculate the molar masses in order to convert to moles. Find the molar mass of copper 2 chloride. Copper is 63.55 plus 2 times 35.45. We get 134.45 grams per mole. Sodium nitrate. Sodium is 22.99 plus nitrogen is 14.01 plus 3 times 16 oxygens. 3 times 16, the mass of 16 for oxygen is 85 grams per mole. And sodium chloride, 22.99 plus 35.45. We have 58.44 grams per mole. And then to figure out the limiting reactant and how much sodium chloride can be formed, we do 2 stoichiometry calculations. We can start with copper 2 chloride. We have 15 grams of copper to chloride. We convert to moles using our molar mass, 134. Just going to make this a little bit smaller. I don't run out of room. 134.45 grams of copper 2 chloride per mole of copper 2 chloride. We use our molar ratio. We have 1 mole of copper 2 chloride for 2 moles of sodium chloride, and then we convert to sodium chloride using our molar mass over a mole of sodium chloride. And if we calculate this all out, 15 times 2 times 58.44 divided by 134.45. We get 13.0 grams, and I should have probably had a bar over the 0, but we should really only be to 2 significant figures. So it's 13 grams. I'll write that over again. And then we do the same thing for sodium nitrate. We start with 20 grams of sodium nitrate. And we convert to moles with 85 grams of sodium nitrate per mole sodium nitrate. We use our molar ratio. We have 2 moles of sodium nitrate on the bottom to cancel out, and 2 moles of sodium chloride on the top. And then we convert back to grams with the molar mass of sodium chloride over a mole of sodium chloride. And we get 20 times 2 times 58.44 divided by 2 and 85. We get 13.7, so actually we get 14 grams. Therefore, our copper 2 chloride is limiting. Remember, draw a little box around copper 2 chloride. That one's limiting. We would have had 13 grams of sodium chloride formed. And D says how many grams of copper 2 nitrate are formed. So we have how many grams of copper 2 nitrate are formed. We're going to look for that. And then I'm just going to keep flipping back and forth so I don't have to rewrite this. Remember, we always need to use our limiting reactant for every single calculation past this. So we start with our copper 2 chloride here. We have 15 grams of copper 2 chloride. We need to use that to determine how many grams of copper 2 nitrate are formed. So we start with 15 grams of copper 2 chloride. We convert to moles with our molar mass, 135.45 grams of copper 2 chloride per mole of copper 2 chloride. We have 1 mole of copper 2 chloride, and we're looking for grams of copper 2 nitrate. We have 1 mole of that, so 1 mole copper 2 chloride, 1 mole of copper 2 nitrate. And then we need to convert back to grams by using our molar mass. If we look up the molar mass for copper, it's 63.55 plus there's 2 nitrogens at 14.01 plus 3 oxygens. Oh, sorry. 6 oxygens at 16. We get a molar mass of 187.57 grams of copper 2 nitrate, all over a mole of copper 2 nitrate. And just double check to make sure everything cancels off, which it does. So how many grams of copper is formed? We multiply this all out. And we get 21 grams. And then it asks how much excess reagent is left over. We need to start again with copper 2 chloride. We always use copper 2 chloride as our starting calculation once we find out the limiting reactant. And we need to figure out how many grams of sodium nitrate we actually needed. We do this again. 15 grams of copper 2 chloride. We convert to moles. 135.45 grams of copper 2 chloride over a mole of copper 2 chloride. We have 1 mole of copper 2 chloride in our molar ratio on the bottom to cancel off. We have 2 moles of sodium nitrate on the top. And then we convert back using our molar mass of 85 grams of sodium nitrate over a mole of sodium nitrate. And making sure everything cancels off. And multiplying everything, 15 times 2 times 85 divided by 135.45. We only actually needed 19 grams of sodium nitrate needed. Therefore, we started with 20 grams, we have 19 needed, we have 1 gram of sodium nitrate left over.